We use the task of shaping the 26 letters of the Roman alphabet as a benchmark to test RoboCraft in simulation. Our method successfully shapes most of the letters in the alphabet. Some of them, such as C and E, are especially challenging targets, but RoboCraft devises a good trajectory to complete the task. To demonstrate the difficulty of the task that we are solving, we invited human subjects to complete the task using the same robot gripper in simulation. We show the results of 2 human subjects shaping the plasticine to C and Z compared with the results of RoboCraft in the simulator. Now we present the data collection process to train the dynamics model in the RoboCraft framework. In each episode of data, the robot applies multiple sequences of actions to the soft object of a randomly initialized shape. For each sequence, the data collection behavior policy randomly samples parameters in the predefined action space. After the robot finishes the current episode, the human resets the shape of the dough into another random shape. We collect 10 minutes of interaction data to train the dynamics model. We will show the results of shaping alphabet letters with a parallel 2-finger gripper. We'll start with the letter R. The target is shown in the top right corner. The robot plans its actions with guidance from a graph neural network-based dynamics model. Since our dynamics model can accurately predict both the rigid and non-rigid motion of the plasticine, the robot still knows where to pinch the plasticine when rigid motion occurs during gripping. The next task is to shape the letter T from a cube. The robot plans 2 grips ahead and executes 1 grip each time. Then it adjusts the plan based on the visual feedback from 4 RGBD cameras. To shape the long tail of the T, the robot rotates its hand to a horizontal position and grips 6 times to achieve the target. This demonstrates our method's capability of solving long horizon tasks. The letter X is easier. The robot accomplishes the goal with just a horizontal grip followed by a vertical grip. Manipulating the plasticine into the letter A is a more challenging task, however. Although the shape of A doesn't seem very complicated, it's hard to shape it from a cube. As you can see, RoboCraft figures out a creative solution to nicely complete the task. The alphabet letters only require the robot to rotate about the vertical axis, but our framework can also accomplish more challenging 3D target shapes that require 3D rotations. The first task is to shape an hourglass from a cylinder. To overcome the issue of kinematic limits, we program the robot to rotate the stand instead of rotating about its vertical axis. After 2 grips, the robot approximately achieves the target, but it decides to pinch again to refine the result. The next target is a 3D X, by which we mean it looks like an X from any direction. The robot accurately predicts how the plasticine will deform and elegantly accomplishes the task. The stamp-shaped target is a more challenging one. It takes the robot 6 steps to accomplish the goal. Finally, we give the robot a pagoda as its target. The robot astutely identifies the cavities in the target and pinches the plasticine at the correct positions. We also compare the performance of untrained human subjects with RoboCraft in the real world. Here we show human subjects' results of shaping the plasticine in the real world. Empirical evidence suggests the proposed tasks are challenging for both manipulation algorithms and human subjects. RoboCraft achieves comparable or stronger performance compared to humans attempting to solve the task with the same robot gripper.